converter changes one type of electrical signal into another. Common examples include alternating current to direct current conversion and direct current to alternating current conversion. Think of a converter as a general term for anything that modifies electrical energy from one form to another. An inverter, on the other hand, is a specific type of converter. It exclusively converts direct current electricity into alternating current electricity. The primary function of an inverter is to take a direct current power source, like a battery, and transform it into alternating current power that can be used by standard household appliances and other alternating current devices. Inverters are commonly found in applications where you need to use alternating current devices when only direct current power is available. For example, in solar power systems, photovoltaic panels generate direct current electricity. An inverter is then used to convert this direct current electricity into alternating current electricity so it can be fed into the power grid or used to power alternating current loads in a home or building. Another common application for inverters is an uninterruptible power supplies. An uninterruptible power supply typically uses a battery to provide backup power in the event of a power outage. The inverter converts the direct current electricity from the battery into alternating current electricity to keep the connected equipment running smoothly without interruption. To summarize, the key difference is that a converter is a broader term for any device that changes electrical signals, while an inverter is a specialized type of converter specifically designed to convert direct current to alternating current. Let's elaborate further on the components and working principles of converters and inverters to provide a more comprehensive understanding. Converters, in their most basic form, can be categorized into several types. Firstly, we have alternating current to direct current converters, also known as rectifiers. These converters typically employ diodes or other semiconductor devices to allow current to flow in only one direction, thereby converting an alternating current input into a direct current output. Secondly, there are direct current to direct current converters, often referred to as direct current to direct current choppers. These converters use switching elements, such as transistors, to chop the direct current input into pulses, which are then filtered to produce a different direct current voltage level. Thirdly, we have alternating current to alternating current converters, also known as alternating current voltage controllers. These converters use devices like thyristors to control the alternating current voltage applied to a load. Finally, inverters fall under the umbrella of converters, specifically direct current to alternating current converters. Inverters use switching elements to rapidly switch the direct current input on and off, creating an alternating current waveform. The complexity of the inverter circuitry can vary depending on the desired output waveform and the application requirements. Now let's delve deeper into the operation of inverters. The fundamental principle behind an inverter is to create an alternating current waveform from a direct current source. This is typically achieved using semiconductor switches, such as transistors or insulated gate bipolar transistors, arranged in a specific configuration. These switches are controlled by a control circuit that turns them on and off in a coordinated manner to produce the desired alternating current waveform. There are several common inverter topologies, each with its own advantages and disadvantages. Firstly, we have square wave inverters. These inverters produce a simple square wave output, which is not ideal for sensitive electronic equipment. However, they are relatively simple and inexpensive to implement. Secondly, we have modified sine wave inverters. These inverters produce a waveform that approximates a sine wave by using multiple steps. They offer improved performance compared to square wave inverters, but they are still not as clean as a true sine wave. Thirdly, we have pure sine wave inverters. These inverters produce a nearly perfect sine wave output, making them suitable for powering sensitive electronic equipment. However, they are more complex and expensive than other types of inverters. The selection of the appropriate inverter topology depends on the specific application requirements, including the power level, the desired output waveform quality, and the cost constraints. In addition to the basic inverter circuitry, many inverters also include additional features such as voltage regulation, overcurrent protection, and short circuit protection. These features help to ensure the safe and reliable operation of the inverter and the connected equipment. Furthermore, Modern inverters often incorporate sophisticated control algorithms to optimize the output waveform and improve efficiency. For example, pulse width modulation is a common technique used to control the switching of the semiconductor devices in the inverter, allowing for precise control over the output voltage and frequency. The efficiency of an inverter is an important consideration, as it determines how much of the direct current input power is converted into alternating current output power. Inverters are not perfectly efficient, and some power is lost in the form of heat due to the switching losses in the semiconductor devices and the resistive losses in the wiring and components. High-efficiency inverters are desirable as they minimize energy waste and reduce the need for cooling. Inverter efficiency is typically expressed as a percentage, with higher percentages indicating better efficiency. Inverters are essential components in a wide range of applications, including solar power systems, uninterruptible power supplies, electric vehicles, and adjustable speed drives. In solar power systems, inverters convert the direct current electricity generated by solar panels into alternating current electricity that can be used to power homes and businesses or fed into the power grid. In uninterruptible power supplies, inverters provide backup power in the event of a power outage, ensuring that critical equipment continues to operate without interruption. In electric vehicles, inverters convert the direct current electricity stored in the battery pack into alternating current electricity that is used to power the electric motor. In adjustable speed drives, inverters control the speed of electric motors by varying the frequency of the alternating current power supplied to the motor. The selection of the appropriate inverter for a particular application depends on several factors, including the power level, the input voltage, the output frequency, the desired output waveform quality, and the environmental conditions. It is important to carefully consider these factors to ensure that the inverter is properly sized and configured for the specific application. In addition to the technical aspects of converters and inverters, it is also important to consider safety precautions when working with these devices. Converters and inverters can operate at high voltages and currents, and improper handling can result in electric shock or other hazards. It is essential to follow all safety guidelines and wear appropriate personal protective equipment when installing, maintaining, or troubleshooting converters and inverters. Furthermore, it is important to ensure that converters and inverters are properly grounded to prevent electrical hazards. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to protect people and equipment from electric shock. In summary, converters are devices that change one type of electrical signal into another, while inverters are a specific type of converter that converts direct current electricity into alternating current electricity. Inverters are essential components in a wide range of applications, and it is important to understand their operation and characteristics to ensure their safe and effective use. Continuing our exploration, it's helpful to understand the evolution of converter and inverter technology. Early converters and inverters were often bulky, inefficient, and unreliable. They relied on vacuum tubes and other primitive components, which limited their performance and applications. However, with the advent of semiconductor technology, converters and inverters have become smaller, more efficient, and more reliable. Modern converters and inverters utilize advanced semiconductor devices such as transistors, insulated gate bipolar transistors, and silicon carbide devices. These devices offer improved switching speeds, lower on resistance, and higher voltage and current ratings, enabling the development of high-performance converters and inverters. Furthermore, advancements in control algorithms and digital signal processing have enabled the development of more sophisticated and intelligent converters and inverters. These devices can precisely control the output voltage, frequency, and waveform, and they can also monitor and protect themselves from faults and overload conditions. The development of high-efficiency converters and inverters has been driven by increasing demand for energy conservation and renewable energy sources. High-efficiency converters and inverters reduce energy waste to minimize the environmental impact of electrical systems. They are essential for applications such as solar power systems, electric vehicles, and energy-efficient lighting. The future of converter and inverter technology is likely to be characterized by further advancements in semiconductor materials, control algorithms, and power electronics packaging. New semiconductor materials such as gallium nitride and silicon carbide offer the potential for even higher efficiency and power density. Advanced control algorithms can improve the performance and reliability of converters and inverters under various operating conditions. Improved power electronics packaging can reduce the size and weight of converters and inverters, making them more suitable for mobile and space-constrained applications. The integration of converters and inverters with smart grids and energy storage systems is also an area of active research and development. Smart grids utilize advanced communication and control technologies to optimize the distribution and utilization of electricity. Converters and inverters play a key role in integrating renewable energy sources and energy storage systems into the smart grid. Energy storage systems such as batteries and supercapacitors can store excess energy generated by renewable sources and release it when needed. Converters and inverters are used to interface these energy storage systems with the grid, enabling them to provide grid support services such as frequency regulation and voltage stabilization. In conclusion, converters and inverters are essential components of modern electrical systems. They enable the conversion of electrical energy from one form to another, facilitating the integration of renewable energy sources, the efficient use of electricity, and the reliable operation of critical equipment. Continued advancements in converter and inverter technology will play a key role in shaping the future of energy and power. Let's address some common misconceptions about converters and inverters. One common misconception is that all converters are inverters, or vice versa. As we have discussed, this is not the case. Converters are a broader category of devices that includes inverters as a specific type. Another misconception is that inverters can create energy. Inverters do not create energy, they simply convert it from one form to another. The output power of an inverter cannot exceed the input power, and in fact, it will always be slightly less due to losses in the inverter circuitry. Another misconception is that all inverters produce a pure sine wave output. As we discussed earlier, there are different types of inverters, including square wave, modified sine wave, and pure sine wave inverters. Only pure sine wave inverters produce a nearly perfect sine wave output. Another misconception is that inverters are only used for backup power applications. While inverters are commonly used in uninterruptible power supplies, they also have many other applications such as solar power systems, electric vehicles, and adjustable speed drives. Understanding these common misconceptions can help to avoid confusion and ensure that converters and inverters are used appropriately. Let's now consider some practical examples of how converters and inverters are used in everyday life. Firstly, consider the power adapter for your laptop or smartphone. This device is an alternating current to direct current converter that converts the alternating current electricity from the wall outlet into direct current electricity that your device can use. Secondly, consider the solar panels on your roof. These panels generate direct current electricity, which is then converted into alternating current electricity by an inverter so that it can be used to power your home or fed back into the power grid. Thirdly, consider the uninterruptible power supply that protects your computer from power outages. This device uses an inverter to convert the direct current electricity from a battery into alternating current electricity to keep your computer running smoothly during a power outage. Fourthly, consider the electric vehicle that you drive. This vehicle uses an inverter to convert the direct current electricity stored in a battery pack into alternating current electricity that is used to power the electric motor. These are just a few examples of the many ways that converters and inverters are used in our daily lives. They are essential components of modern technology, and they play a crucial role in powering our homes, businesses, and transportation systems. In closing, the distinction between converters and inverters lies in their specific function. Converters are general devices that change electrical energy from one form to another, while inverters are a specialized type of converter dedicated to transforming direct current into alternating current.